Well, a warm welcome to everybody. Come on in, get your notebook ready, get a pen, get a pencil, whatever it is you want to write with is fine. This is math from the void. Math coming at you out of nowhere. And today we have a problem from the 1991 AP Calculus BC exam. Now, despite it saying BC, if you were in an AB class, I think you'd be able to find all of the solutions to this question attainable. Yeah, looking at the question, it looks like there wouldn't be any problems here. They give us a particle motion. They tell us that its velocity is given by this equation. So this is how fast the particle is moving, as well as what direction it's moving in. And they give us this initial condition. They tell us that at time equals 1, the particle is at the origin. In other words, x of 1 equals 0. Okay, great. So they want us to find the position x of t, which is going to jump straight into integration. So we're going to jump straight into saying that x of t is the integral of the velocity. You get a point for noticing that and saying that. Now let's actually take the antiderivative, the integral, 36t plus 15. And we just do some simple power rule stuff with it, right? Raise the power by 1, divide by the new power. Raise the power by 1, divide by the new power, t squared, plus 15t. And then we have this plus c. The initial condition is what's going to help us with plus c. We know that if you plug in a 1, you should get 0. So this is simply 4 times 1. Any power of 1 is just 1. 4 times 1 minus 18 plus 15 plus c. This has to equal 0. And that's 19 minus 18, which is 1 plus c equals 0. That means c equals negative 1. So the position function is as follows. X of t equals 4t cubed minus 18t squared plus 15t minus 1. All right. Very nice, very nice. Find the values of t. Very interesting. They want us to find values for t. That's our final answer. When the particle is at rest, which means v equals 0. So we have to find out when the velocity is 0. And we see that it's a quadratic. It's probably factorable. Let's check it out. Yes, v of t is absolutely factorable. If we go old school with this, let's go old school with this. We can find what multiplies to 12 times 15, which is 180. But it adds together to give us negative 36. How about negative 30 and negative 6? Yeah? In fact, we could even factor, now that I think about it, we can factor 3 out right from the get-go. And we would have 4t squared minus 12t plus 5. I want to find out when that equals to 0. Even more doable if we do this old school method again. What multiplies to 20 and adds to negative 12? How about negative 10 and negative 2? So we could factor this by grouping or any other method that you like. I'm being kind of lackadaisical here just because I'm not in a rush. So if we factor this, we have 3, of course. We have 2t, leaving us with 2t minus 5. And then we'll take out a negative 1, also leaving us with 2t minus 5. So that's going to leave us with factors of 2t minus 1, 2t minus 5, and we can find when each of these factors equals to 0. This is going to be, of course, when t equals 1 and then over 2. This is going to be when t equals 5 and then over 2. So those are our times. Particle at rest. The velocity is 0. Okay, that answers part B. Very straightforward. All we really did was use the interpretation of particle at rest. That does give us a calculus interpretation. That means the velocity is 0, or a physics interpretation if you're in physics. And then you just have to find what are the values of t that make this 0. So it's the same thing as solving a quadratic equation. An Algebra 2 student could do it. Next, let's find the maximum velocity. We want to find the maximum value of this, and they give us an interval. So we're looking for like the absolute maximum. So we're going to have to use methods for finding absolute extrema, absolute maximums. Well, if we're on an interval, the only candidates that we have for maximums and minimums are the endpoints. So the endpoints of the velocity, that's going to be when t equals 0 and when t equals 2. We'll plug those into C. But also the critical points. So we're going to need the derivative of the velocity and set that equal to 0. So not when does the velocity equal to 0, but when do the critical points come up for the velocity. So when is the derivative of the velocity equal to 0, which we haven't done yet. Let's first check the endpoints by just plugging in these endpoints. You can plug it into the factored form, or you can plug it into the raw form up on the top. Either way, you're going to get 15 when you plug in a 0, right? Because it's like 0 squared is 0, 36 times 0 is 0, plus 15. And remember, we're plugging this into the velocity, not the position. We want to know about the velocity. So even though part A had us go backwards into the position, we don't really care about that. We care about the velocity here. And then let's plug in 2. What is that going to give us? That's going to give us 3 times 2 times 2 minus 1, so 4 minus 1, times 2 times 2 minus 5, so 4 minus 5. That's going to give us 3 times 3 is 9, times negative 1 is negative 9. So far, we have a lowest velocity and a highest velocity on the endpoints, but we still have to check the critical points. Okay, so let's take a derivative of the velocity. V prime, just in time. It's going to be 24t minus 36, and we're going to set this equal to 0. We could factor out, divide out 12 if we want to, and this leaves us with 2t minus 3 equals 0. So when t equals 3 halves, we have a critical point. Now, we don't know if 3 halves is going to give us a maximum or a minimum, or do we? It's going to give us a minimum because the velocity is an upwards facing parabola, and so its critical point can't possibly give us a maximum. Okay? In fact, I can even go further and say the second derivative of the velocity equals 24, which is positive, and that means that v is concave up, and that tells me that the critical point is a minimum. So I don't even have to calculate it. Ha! Got around it. I don't have to plug in 3 halves. I can just say not important. It's some minimum. We just know that it's some minimum. It's definitely lower than these two. So the maximum velocity is going to be v equals, what did we get? 15. And we can go ahead and say at t equals 0. Okay, and then since we kind of wrote all over this here, let's sort of move this stuff. Yeah, we want to move all of this. Move all this work. Oh, my 20. Take my 20 with me. Let's move all that stuff over there. That's a little cleaner. It gives us some space to work on part D and to read it. Find the total distance traveled from 0 to 2. Total distance means we need to know the absolute value of the velocity. We need to know when is the velocity negative and when is it positive on this interval from 0 to 2. So we can do that by taking our factors, all the stuff that we moved, this velocity function, and we can go ahead and put this on a chart. Yeah, good old chart saves the day, as usual. So we have 3, which is always positive. We have 2t minus 1, which follows normal sign behavior. 2t minus 5, which also follows normal sign behavior. Thing is, the 0 for that one is beyond our interval. We're only caring about this from 0 to 2. 3 is always going to be positive, no matter what t is equal to. 2t minus 1 is going to be 0 there, negative beforehand and positive afterwards. Similarly with this factor, and the product, the velocity is the product, which means that we're going to have positive, then a negative, then a positive. But our region cuts off at 2, so really we only care about what's happening from here to here. If you notice that the velocity is negative from 1/2 to 2, that means that for the total distance, we're going to have to take that integral value and subtract it. It's going to be a negative integral value. We need to turn it positive. So we want the integral from 0 to 1/2 of the velocity. But then we're going to subtract this distance from 1/2 to 2, because 1/2 to 2, they're going backwards, but we want to add that distance. So we need to subtract the negative value of the integral. And since we already did the antiderivative, this will be pretty easy. This is just going to be x of 1/2 minus x of 0 minus x of 2 minus x of 1/2. So altogether, we're going to get 2 x of 1/2 minus x of 0 minus x of 2. That's going to give us our total distance traveled. Let's see if we have the values of that anywhere. We don't, but we have the equation. So let's go ahead and write the values here. Of course, x of 0, we do have x of 1, the initial condition, but that's not going to help us. X of 0 is -1. Let's see what x of 1/2 is. This will probably take us the longest. We're going to have 4 times 1/2 cubed minus 18 times 1/2 squared plus 15 times 1/2 minus 1. And let's work that out carefully, shall we? So this is going to be 1/8 times 4 minus 18 times 1/4 plus 15 over 2 minus 1. I think these are all going to simplify nicely to something over 2. So this is 1 over 2. This is 9 over 2. 18 over 4 is 9 over 2 plus 15 over 2. And then we can just call 1 2 over 2. So that wasn't too bad. Let's see. 1 plus 15 is 16. 9 plus 2 is 11. 16 minus 11 is 5. So we have 5 over 2 is x of 1/2. -1 is x of 0. And lastly, we need x of 2, which is going to be 4 times 2 cubed minus 18 times 2 squared plus 15 times 2, and then minus 1, which is nice. This is just 4 times 8, which is 32, minus 18 times 4, which is 72, plus 15 times 2, which is 30, minus 1. So this gives us 62 minus 72 is -10, and then minus 1 is -11. So let's take these pieces and plug them into our total distance. 2 times x of 1/2, that's going to be 2 times, what was it, 5 over 2? Is that correct? I don't want to mislead. Yes, 5 over 2 minus x of 0, which was -1, so minus a -1, minus x of 2, which was -11. Okay, great. So we have 5 plus 1 plus 11, or 17. That is the total distance traveled. Fascinating. So these total distance problems all come down to how quickly can you determine which regions are negative velocity and which regions are positive velocity. That way you can account for that when you take the integral. You cannot take the integral of the velocity without checking if it's negative at some portion. Otherwise, you're not going to get the total distance. You're just going to get the net change, the displacement. Meaning if the velocity has the object go forwards and then backwards, and you say, okay, well, it only went from here to here. No, that does not count all of this positive distance and then also count all of this negative distance as a positive value. Instead, what that does is that takes all of this positive distance and subtracts this distance. And then we have the overall displacement, which is fine if we just want to know how far do we end up from home. But if we want to know the total distance traveled, we have to be more careful. Okay, that's enough blab out of me. Hope you had a good time. Thanks for joining us here. I'll see you next time in the void.